Okay. Yeah. We are going to start in 1 minute. Okay, so welcome everybody to this morning's session about quantum error correction. The first talk this morning is about efficient soft output decoders for the surface code. This is work by Nadine Meister, Pattison, and John Preskill, and Nadine will give a talk.
Yeah, thank you. My name is Nadine, and today I'll talk about some work that started last summer with Chris and John at Caltech.
The first talk this morning is about efficient soft output decoders for the surface code.
I'll just keep going. Okay, so first we'll give a little bit of background and introduction on the surface code decoding, and then how we can turn those decoders into soft decoders, and then some numerical and analytical results. And then finally, the applications of these soft decoders to other relevant quantum information tasks. And finally, we'll conclude. Okay, so the error correcting code that we studied was a surface code, and it consists of these data qubits as these like blue circles, and they all represent like one logical value. And so say we're trying to correct some errors on these data qubits or figure out what errors happened on these data qubits. We have these Z and X checks to check for X and Z errors. And they're just a product of the Z or X stabilizers on the neighboring qubits. And so, for example, if there was an X error at one of the data qubits, then that doesn't commute with the neighboring Z checks. And so those ones will produce some non-trivial syndrome results. And so how do we fix these errors? That's where the decoding part comes in. We oftentimes construct this decoding graph. And so here we've done it just for the Z checks, so all the nodes are Z stabilizers, and all the errors are these these error mechanisms on these data qubits. So these like an X error on a data qubit, and an edge connects two nodes that it would, for example, like light up. So now let P be this individual physical qubit error rate. So basically in this Z check decoding graph, that would be the probability that each of these like data qubits has an X error. For this P, we're going to define the edge weight to be the log likelihood ratio of P. And so given this graph, now we need to come up with some algorithm or some decoder that'll tell us, okay, I see that there's some error happening near here. I want to figure out which data qubits had that error. And so the two most popular ones or most common ones for the surface code are this like minimum weight perfect matching decoder and the union find decoder. And the minimum weight perfect matching decoder works kind of exactly as its name sounds. Say we had some more errors, and so some more checks had some non-trivial result. Our minimum weight perfect matching decoder is going to try to find a perfect matching for all these red nodes, all the non-trivial ones. And so that just means like some pairing, some matching between these red nodes that has total weight as low as possible. And so for this example, that would just be saying, okay, this data qubit had this error and it lit up those two, and this data qubit lit up those two. Okay, and so the union find decoder works differently. It's an almost linear time decoder, and it has two steps. The first is converting this bit flip decoding problem into an erasure decoding problem. And so where an erasure is this like third kind of error, an erase bit that we can represent as either identity or X error with equal probability at a specific known place. And that's kind of the key part. And so how do we convert this into an erasure decoding problem? We, again, start with our decoding graph with our non-trivial syndromes. And we start growing clusters around the red nodes. A little hard to see, but there are these like beige circles around here that where basically we are growing this this erasure region. And so this like in this step, we like grow this erasure region to basically denote that all qubits near here and near here are now going to be denoted as erased. So they're either going to be identity or X at specifically these places. And in here, maybe it's impossible to see, but the clusters have grown such that they have merged. And we stop growing when all the clusters have merged, and specifically when there's an even number of red nodes inside a cluster. Yeah. Pretend the cluster is like that. Okay, and so lastly, then you want to correct the clusters as erasures inside. And so lastly, like after you've merged all your clusters, you can correct them as erasures, which means you can like just find any correction within the clusters that satisfies the syndrome. Okay, so these are just two decoders that return either like a yes or a no result. This is a logical failure, this is not a logical failure. But we actually want to also output maybe like how sure the decoder is that it failed. So for example, I'm like 80% sure that I've produced a logical failure or not. And so in order to do that, we want to extract some soft output, we will call it phi, which approximates the probability that the decoder failed. And to do so, we have come up with this algorithm where we essentially set all edge weights within the cluster to be 0. So pretend the clusters are here. So all edges inside there are 0. And then we want to find this minimum path between the one boundary to the other boundary. And then we'll define phi to be the sum of like the two, well, basically the path that's left over. And so the intuition for this is that in our union find algorithm, we were growing these like erased regions that we're gonna call all the data qubits in there erasure errors now. And so we're essentially just like literally erasing them here by setting this edge width to 0. And why do we look at a path between inequivalent boundaries? Because in a surface code, that denotes a logical failure. And so basically when we were saying everything in here has been erased, like what's left, how uncertain is the decoder now? Okay, so this makes sense for union find because the clusters in union find, even though you can't see them, are extremely important and like a crucial step in the algorithm. But for minimum weight perfect matching, it's not clear what a notion of clusters might be. But there is this work by Yo done in 2022 where he kind of showed that, or like found this like analogous cluster idea in minimum weight perfect matching. And I guess the main idea is that minimum weight perfect matching can be formulated as a linear program where you're trying to minimize something, exactly as the name sounds. And its dual linear program is formulated as follows as well, where now we're trying to maximize the sum of these dual variables under the constraints that they all must be greater than 0, and this like new slack definition also has to be greater than 0. And so what is this slack of E? Now we're going to look at all edges E between non-trivial syndrome nodes, so between these red nodes, and we need to say that this slack must be greater than 0, defined as the weight of this edge minus kind of all the YS's that like overlap this edge. And so from there, you can kind of see how maybe these YS's denote clusters and that this YS is the radius of the cluster. So I guess the main idea of this slide is that clusters do exist in minimum weight perfect matching. And so then we can use our algorithm that we've defined before to also extract soft output information. Okay, and so this is just like an algorithm that we came up with that extracts soft output, but we don't know if it's actually correlated with the decoder, with the decoder failing. And so we ran some numerics to kind of see this correlation. And so here we have a surface code that we've, oh no, okay. Oh yeah, we ran some simulations where this surface code has phenomenological bit flip noise. So every single qubit has the same probability of having an X error. And we were able to show this like pretty correlated, pretty nice correlation between phi, that path length that we defined before, and the log likelihood ratio of the probability that the decoder returned a logical failure given the syndrome. Okay, so these are just numerics though. So we want to see, can we prove anything about it analytically? And so first we looked at the repetition code, kind of like an easier version. And we were able to actually show that this is an equality here. And how this theorem shows that, here consider the, okay, so consider we have a repetition code with here 1, 2, 3, 4, 5.
Did you manage to sleep yesterday?
I think I did.
Okay.
Yeah. But better than
with
last time was like a
with
terrible, like
5
so many people and
with 5 qubits
so
in the
many
repetition code.
garbages. Yeah, we
And-
understand we shouldn't use a pet bottle now.
And okay, so let the
Yeah,
let's go.
because
Okay,
they
so
have
this
to
repetition
view
code
the-
has some
yeah,
error.
right.
Like
Yeah, yeah.
industrial
I don't know, should I do
garbage.
something about it?
Like what is the business? Like kind of.
Yeah.
So like my husband's parents had
I
like a
also slept
business
very
in
well last
Napa.
night.
Yeah.
And their garbage doesn't need to care anything because it's industrial garbage and they take everything.
Okay,
even though
and
it's
so
mixed.
the error, there's some error that happened here, and it produced this red syndrome. And so the output of the decoder is, we're going to call this orange line right here.
The SDGs are
And
always written somewhere.
We
and
were able to
have
show
fill.
that the
And
probability
it's
that the
daily,
error
right,
was
for us, so
actually
we
this
do,
orange line
but we don't
is
do like
divided by the
300
probability
one
that
at the same
it's
time.
not that orange line.
Okay, I didn't know that. Yeah, we
The log of that ratio is exactly this phi value that this soft output value that we've defined before.
Audio, which
Where it's like the distance from one boundary to the other boundary with like everything inside set to 0.
Zoom or YouTube?
Okay, and I guess how is this actually showing this relationship back here? So it's because in the repetition code, there are really only 2 options. It's either this orange or this green. And so essentially this denominator is the probability that there's a logical failure. Because if the error was actually equal to this green, but the decoder outputted this orange, that like forms like basically the decoder has flipped the orange line and the real error has flipped all the other lines, and that's like a path from one end to the other, a logical failure. So this denominator here is a logical failure, and similarly the top is 1 minus PL. And so I guess kind of like the intuition and maybe like what's cool about like this result is that because of the way like log and division and probabilities work, we're really just showing that the weight of this green, so 1, 2, 3, 4, minus the weight of this orange, 1, is 3, which is out like the weight of the soft output information. That's like essentially all we're showing here. Okay, so that was just for the repetition code. Now we want to show it for the surface code as well. And I guess unfortunately, we were only able to show just like this lower bound. But it's like in a similar manner where we've defined F to be the decoder's output and M to be the output of the opposite logical class. So if you were to combine this orange and the green, we would again have like a path from top to bottom. And so we have to show that the log of the probability that the error is actually the one that the decoder outputted over the probability that the error is the minimum weight 1 of the opposite logical class is greater than or equal to phi. And I guess one thing to note is that we also really wanted to show this with these logical classes, not just F and M. But hopefully like this is like ideally this is a good approximation. Oh yeah, and again, pretend there's clusters around the red dots. Okay, and so what are the applications of this soft output? This first one was really like the inspiration for this, like coming up with a decoder that produces soft output. And it's for improving decoders of concatenated codes. And so specifically the hierarchical code. specifically the hierarchical code, where the hierarchical code is a concatenated code with 2 layers, and the outer layer is an LDPC code, and the inner layer is a surface code. So each of those like physical qubits in the LDPC code, if you kind of like zoom in, then you would see a surface code. Each of those is a surface code. But yeah, see Chris's talk tomorrow on hierarchical codes. But essentially, it's a way to use a good quantum LDPC code if you're restricted to geometrically local gates. Okay, and so when we ran basically just like belief propagation on this outer decoder, and we didn't pass any information. We just decoded the surface code, maybe got like a 0, decoded this one, got a 1, and just passed that information into the outer code, then ran BP on that. That's what we see in this orange line. That's how the logical failure rate of the outer code scales with the inner code's failure rate. But if we include the soft information, so maybe we return like a logical failure with like 10% or no logical failure with 100%, and passing that information through, that's where we get this blue line. And we can see that, okay, maybe you can't see it, but there are dotted lines to represent the pseudo thresholds, like around here and around here. And so we can see that the pseudo thresholds improve by a factor of 2. Oh yeah, and also to note that this error floor, we just use BP, and so that's like any message passing algorithm will eventually hit an error floor. Okay, there's also supposed to be a histogram here, but the second application is for error detection. And so basically, if you're trying to perform some circuit sampling task and you want it to be super accurate, you want it to be really accurate, then you would maybe construct this large error correcting code that has, so in order to have a very low error rate. But what we show here is that you can actually do the same with a smaller error correcting code, and you just have to discard these runs with low phi values. So for example, here, I think I can actually pull up the PDF too. I don't know, maybe that's not a good idea. Okay, it's fine. But basically this, imagine the sample distribution of phi is kind of like, wee. And if we discard just the very low values where the phi is 0, and phi being 0 is basically where the decoder is like, I have no idea, 50-50. So if we discard values where the decoder was uncertain, then we can see an improvement in the logical failure rate by an order of magnitude, and we only discarded like 10 to the -4 of the data. And so the idea is that you can choose how much data you want to discard and increase your logical failure rate in that way, or decrease your logical failure rate. Okay, so in conclusion, we were able to construct an efficient way to extract the soft output in surface code decoders. And in doing so, we improved the decoders of concatenated codes and improved some circuit sampling tasks. And in the future, it would be cool to come up with more efficient soft output algorithms for other error correcting codes, and also a tighter or the other bound for the surface code result. Okay, lastly, thank you to, I worked on this project with Chris and John, and Chris was my main mentor throughout the project and taught me everything about error correction, hierarchical codes, and soft output, and was like a main driver on this project. So huge thank you to Chris. And yeah, we were working at Caltech last summer. Thank you.
We have questions. Okay.
Thank you for the wonderful talk.
Mm-hmm.
So I'm really curious about these concatenated constructions. So do you happen to know how can decoders like BP take into account the soft information? I'd love to understand this better.
Okay, yeah. So here, BP has like an initial starting value, and then it passes its information. I guess if you were to visualize the checks on this side and then the bits on the other side, it has some initial starting value for initial guess for all the bits. I think that value is really just 1/2, 1/2, 1/2 for everything. And so then you pass the information back and forth and you reach a, like, pass that information to the checks, pass that back to the bits, and then you kind of update your like probability of your bit failing, essentially.
So it's really quite simple.
Yeah, and so now we just change the starting value. Exactly.
Oh, thank you very much.
Yeah.
Thank you very much. I just wanted to ask you whether you can use this soft information just for the surface code decoding, right? So this gives you some confidence, you said, about whether your recovery is basically correct or not. Can you use something if the confidence is greater than 1/2, keep it if it is lower, change it, and does this improve the threshold or something? Have you looked at this?
The threshold of
the MWPM decoder.
Well, like the MWPM decoder will output the bits that it maybe. Okay, it'll output the bits that it thinks has failed, and then whether or not those give a logical failure or not. And so, okay, basically like maybe more details on how the simulation was run, and maybe that'll answer the question. Here we would sample the surface code with this, like each bit having some probability of failing. Then we would run minimum weight perfect matching on it. It would tell us, we would like have its clusters and everything, and it would tell us whether or not it's a logical, like whether or not it failed or not. So maybe for like this phi value, in this instance it failed, and in this instance it didn't fail. And when we like collect all that data together, that's how we kind of form this curve. And so if we want to improve this threshold, then yeah, we can just like take out any values with low phi values, and then it will.
And then flip it, yeah?
Sorry?
So if phi is low, you have low confidence, right?
Yeah, and then we could just throw it away, and
Yeah,
then we would only be left with values that have.
Yeah. And maybe just another question. So when you think about this correspondence, do you think it holds beyond the bit flip noise? Like if you have more complicated noise?
Yeah, so I guess we just ran bit flip noise because in surface decoding, you like decode the X and Z separately.
Yeah.
But like, yeah, if you had both of them, then for sure. Yeah. Thank you.
Other questions? I have a comment and maybe a question also. So somehow what you are doing here, you have actually a good estimator actually for the probability of decoding failure of the underlying binary linear code. Somehow the troy code can be viewed as a hypergraph product code with associated repetition code. And basically what you did about repetition code, you found a good estimator actually for the decoding failure probability somehow. So have you tried to generalize the result actually to the hypergraph product construction and try to look at what could be a good description actually for the decoding failure probability for the underlying code actually?
Okay.
I mean the classical code? It's kind of natural to do this here.
Yeah, I guess our like algorithm relied on this like cluster idea. And so
Yeah.
if the hypergraph product code like decoder doesn't have this cluster, then I'm not sure how you would apply this directly. But I know that there's like the logical gap stuff where it's like, it is more general, but it's like not efficient, where essentially you are just like calculating F and M and then like taking this ratio. And so like basically like you find what did the decoder return, and then what is the next closest, like basically like calculate M, then take that ratio. That would like also work. And I think that's like this logical gap thing. But yeah, like it's just not efficient. But that's like how people have generalized it.
Okay, I see. Okay, thanks. Don't have any question. Let's thank the speaker again. Going to start again in 5 minutes, just to make sure that we are on for power sessions.
I'll have to change to the other screen. Download.
No. Because it's already downloaded actually.
Oh.
So I think
Maybe go to the download page. Not this one here. Yeah. The folder.
Folder. No, because this is not the download. It
Oh.
is actually this is the on what is on the server.
But if you try to open this one, would it work like the upper one?
Yeah, actually, what we did, we downloaded it.
Yeah, let me try.
Wait a second.
I think it worked.
You managed to do it?
Yeah.
It's there now. Okay. It's okay.
That's good.
Okay. Okay, so we are going to start with the last talk of this session, which is about multi-qubit lattice surgery scheduling. So this joint work with Silva, Webb, Yang, Lemieux, Scherer, Zhang, Kramer, Liu, Chen, Ronagh, and Allyson Silva will give a talk.
Thank you for the introduction. So, hi, everyone. My name is Allyson Silva. I'm a full-time scientist with a background in operations research, working at Multi-qubit, which is a quantum computing software company based in Canada, where this research was developed with a multidisciplinary team of quantum researchers and software developers. Today, I'm going to present our paper titled Multi-qubit lattice surgery scheduling. I will begin with a short summary of our work, and I will detail the research that we conducted, culminating the key takeaways derived from our observations. So here's a summary of our research. In it, we explored the optimization of multi-qubit lattice surgery, which is a promising technique that can be used to perform logical operations by connecting distant qubits in topological error-correcting codes. A problem arising from lattice surgery is the lattice surgery scheduling problem, as we call, or LSSP, as I'm gonna use in short in the rest of the presentation. In this problem, we need to make decisions related to the order, this basically the sequencing of the, in which the logical operations in a quantum circuit should be executed, and also the logical resources, resources required to entangle the qubits requested by each one of these operations using lattice surgery. We model mathematically this problem and used a heuristic solution for it because of the scalability requirements to solve it. And then we run our algorithms to generate a scheduling for operations of circuits that were generated inspired by real, possible real applications. So we could investigate metrics such as the expected runtime needed to execute these operations and the parallelization potential of the operations in these circuits. We also analyzed the trade-offs in the scheduling of these circuits after a transpilation algorithm that is known in the literature that reduces the number of logical gates in circuits at the cost of increasing their weights, basically the number of qubits requested by each one of them. So in a brief summary here about topological codes and logical qubits, first of all, probably most of you should know about this, but fault-tolerant quantum computation aims to ensure reliable quantum computing despite the presence of the current faulty physical qubits. So the solution for it is using quantum error correction codes, which present some techniques, including the topological codes, for enabling this fault-tolerant quantum computation. Two-dimensional topological codes usually encodes quantum information into logical qubit patches, similar to these ones that you see on the side, which are protected using rounds of parity checks. So basically, we get like a single physical qubit, we arranged in a organized way to form a patch that I'm going to be representing by these squares here. And these patches are located in a two-dimensional lattice, which is similar to a chessboard, you can say like that. And they occupy tiles, which can be like a single tile, such as this one, or maybe two tiles, such as this one. Or we can even have like some other combinations, such as two qubits occupying a single patch, but in two tiles. Talking about the circuits that needs to be scheduled, the error lattice surgery considered requires that all logical operations are in the form of polyrotation measurements. A polyrotation measurement is represented by a poly operator, P, as you see here, and a rotation angle, theta, as you can see on the side, which for the code considered must either be a pi4 rotation or a pi8 rotation. Operations in other gate sets, such as, for example, the Clifford plus T universal gate set, can be easily converted to polyrotations using these conversion rules. And other gates, such as, for example, arbitrary angle rotations, can be approximated using decomposition techniques, but this is beyond the scope of my talk here. So we are given a circuit composed of polyrotation measurements on the side that can be represented as a matrix, where each one of the rows represent a single rotation that needs to be performed, and the columns represent each one of the qubits requested by them. By defining a commutation rule, for example, as the trivial commutation rule, we can build a graph that we call as a dependency graph, representing the dependency constraints for the execution of these operations. So, for example, in the trivial rule, as I mentioned, it says basically that, let me get one example here. So for the second operation and the third operation, given that they do not share a single qubit requested, so for example, first qubit is only requested by this one, second is only requested by the second one, and so on, remembering that the identity operation, we consider that means it's not requested, then that means that 2 and 3 could be executed in parallel, in theory, because they commute. So in this example here, as I mentioned, like 2 and 3 can be executed in parallel. 1, no, 4, no. That means that we have 4 operations, but the depth of the circuit is 3. With that, we define a metric, which we call the average width of this dependency graph, that defines the parallelization potential of the circuit. In this case, 4 divided by 3, 1.33. So lattice surgery in topological codes means that a multi-qubit logical gate between adjacent 2-dimensional topological patches involves multiple rounds of parity checks. So lattice surgery can be executed by measuring stabilizers between the edges of the logical patches, meaning that we only need to create like these kind of connections between the patches of the qubits that are requested in the circuit as I showed before, in order to perform that operation. So I give here one example of how this is done, just a simple example so you can understand. So let's say we have like these 2 operations, a pi4 rotation, a pi8 rotation, sorry, requesting the y and y operators of the qubits 2 and 3, and a pi4 rotation requesting the x of first qubit and z of the 4th qubit. In order to perform these 2 operations in parallel, we need to generate like the ancilla patch, as we called for the lattice surgery, using the quantum bus, which are these green tiles here, that connects these qubits, so qubit 2, qubit 3, and because this is a pi8 rotation, it needs to connect to a magic state storage qubit, using only the quantum bus, and none of the bus tiles could be shared by the same ancilla patch. So if this is possible, then we can guarantee that these operations can be executed in parallel. So given the circuit and the topological layout, we can define the lattice surgery scheduling problem. In overall, when we are designing any fault-tolerant quantum device, we should optimize space and time costs. Space cost refers to the quantity and arrangement and possibly other measurements that are related to the qubits, to the logical and the physical qubits, while the time cost refers to the expected runtime for the whole circuit. So given a topological code layout representing where the operations will be executed, the lattice surgery scheduling problem tries to minimize the expected circuit execution time by searching the operations that can be performed in parallel. Also, this problem, when we are solving it, indirectly reduces the space costs because we are trying to generate ancilla patches for the lattice surgery that are of the smallest size as possible. And because we are using fewer qubits, that may end up like resulting in smaller encoding requirements for the logical qubits in the end. We searched on the literature about this problem, and we found that this is not new. There are like many studies that solve this problem in the literature, but they usually consider only the connection between 2 qubits, so pair of qubits. This is relatively easy to solve from an optimization point of view because this requires solving shortest path problems to parallelize these gates. But I will show later that because of the transpilation algorithm that we run, there are like a higher likelihood that the operations will become like larger, will require multiple qubits. And for that, for generating the connections between these multiple qubits, we are required to solve shortest 3 problems. Okay, so this is a classical NP hard problem in the optimization. All right, so given the problem, we first try to model mathematically it. Don't worry about this math here. This is just like a candy for the math lovers. But what is important for you to get from it is that we can decompose this problem between 2 different, let's say, like models. The first one, like the higher level model, is what we call the sequencing decisions, is what does the sequencing decisions. In this model, we are interested in minimizing the number of packs of operations that can be scheduled in parallel, where a pack represents like a set of operations that respect that does not involve any contradictions regarding the commutation rules. And given a certain pack of operations that are candidates, we try to solve the sub-problem that generates the trees that connects the qubits that are requested by each one of these operations and seek for a feasible solution for these packs also minimizing the number of bus tiles that are used for the construction of these trees. So in a quick example here, again, given the trivial rule, these two operations here commute. So that means that this is a candidate pack for the primary problem. So when I go to the sub-problem, I need to generate like 2 ancillary patches, one for each one of them, that connects all the qubits requested. And if it's possible, if there is no bump between the Silva patches, we have a feasible solution. The problem with that model is that it requires generating all the combinations of packs, which increases exponentially. And this is very costly computationally. So instead of that, and because we need to schedule like millions of operations, even more on a real quantum circuit, we developed a heuristic algorithm, very simple one, a greedy heuristic as we call it, to solve this problem using known methods from the optimization point. So we are given first here as an input the circuit that needs to be scheduled in the form of a dependency graph, and the adjacency graph representing the adjacencies between the logical qubits in the lattice. So we identify the dependencies among the operations to build this dependency graph, and then we run a loop where we identify the candidate packs from the dependency graph. So in this case, the candidate pack will be composed of all the operations that are the root nodes of this dependency graph. Oh, sorry. Yeah, and then for these candidate operations here, we generate the trees connecting the qubits that they request. So for example, here, I need to connect like the X operator on the qubit 2, so this one here, and the Y operator on qubit 3, so Y is basically X and Z. And because this is a pi4 rotation, I'm connecting to ancillary qubit here on the side. So for that, we solve a Steiner tree problem, which, as I mentioned before, is a classical NP hard problem. And this example here, I only have one operation to be packed, but if I had another one, I could just remove like these nodes that were used and search for, solve again this Steiner tree problem for the remainder of the operations, given the updated adjacency graph. So we repeat this operation multiple times for always updating the dependency graph to grab like the next candidate pack. Again, like every time that these are scheduled, I remove these operations, I repeat this loop here again, and in the end, we expect to return the operations that were scheduled, given a certain order, and the trees generated for these multi-qubit operations. So for the computational experiments we performed, we generated random circuits and, as I mentioned before, like real-world inspired circuits using Hamiltonian simulation. Here's a list of the applications that we consider. I'm not a specialist on quantum algorithms, so if you want to ask anything about it, probably I won't know the answer. But from this list here, we generated circuits with up to 18 million Pauli rotations and up to 50 logical qubits, data qubits. So basically these purple tiles here. And to facilitate parallelization between the operations, we consider this layout for the algorithmic area, the core of the device, because we have like multiple ways to connect the different qubits using the quantum bus. Before I show you results about our experiments, I want to briefly talk about the transpilation algorithm that we run and which inspired the development of this method. This transpilation algorithm is inspired by this study here, the Lattice 2019. It's relatively simple. So we get the input circuit composed of pi4 operations and pi8 operations. And then we perform these 3 steps to remove all the pi4, all the Clifford operations from the circuit, and to try to reduce the number of pi8, the non-Clifford operations from it. So first we push all the pi4 rotations, so we perform a sort of like sorting algorithm here. Then we reduce the number of pi4 and pi8 layers by combining operations whenever it's possible. And finally, we commute pi4 rotations past the qubit measurements, of course, updating these qubit measurements in order to end up with a circuit like that. That has a reduced length. One known feature of this algorithm is that when we are doing this first operation here, pushing the pi4 rotations, I have an example here for like pi4s here and pi8s here. When we do the commutations for the pi8s, they tend to become like heavier. So they tend to require more qubits once I commute them. So in the literature, I brought like this quotation, this citation here, that highly parallel input circuits can become serialized with prohibitive runtimes because of this algorithm. So we investigated this affirmation by running our greedy algorithm for circuits before and after transpilation and comparing the solutions obtained for the scheduling problem. And the results are summarized here. So let me briefly go over them. So the first one that you see, the circuit length, refers to the number of operations in the circuit. So you can see that on average, we had 5 million operations before transpilation, and we end up with 500,000 approximately, which means a 89% reduction on average. Circuit length is composed of pi4s and pi8s. I'm ignoring the measurements for now. And I just want to show you here that after transpilation, we remove all the pi4 operations, but we also reduce the number of pi8 operations, which is good because these are the costly part of fault-tolerant quantum computation, by 72% after running this algorithm. Again, as the literature knows, as this is vastly known, the number of qubits requested by operation increases after running the transpilation. Consequently, the parallelization potential, average width of the circuit, decreases because we have like fewer parallelization opportunities. But we show that despite of this reduction in parallelization potential, the reduction on the circuit length outperforms this. So we end up like with 87% reduction in the number of logical cycles to execute all the operations remaining in the circuit. This second last one here is just like the wall clock time. I just want to show that the problem becomes much easier to solve. The scheduling problem becomes much easier to solve after transpilation as well. Again, because we have like a smaller circuit and because we have fewer parallelization opportunities. But something very interesting is that even despite of like running the transpilation or not, there are like parallelization opportunities in both circuits as we observed. So in the pre-transpiled circuit, we observed that comparing this solution here, the number of logical cycles, to the circuit length, we could still parallelize approximately 37% of the operations. And even after transpilation, we could still parallelize 21% of the operations. And some other very interesting thing that we observed is that the lower bound solution for the scheduling problem for the pre-transpiled circuits, meaning the circuit depth, is still higher than the upper bound solution for the scheduling problem for the post-transpiled circuits. So that means that even if we could not parallelize any operation in the post-transpiled circuit, that would still mean that the number of logical cycles for the post-transpiled circuit would be reduced compared to non-transpiled circuits. So in conclusion, I just want you to take like these two takeaways from this presentation. The first one is that solving this problem, this lattice surgery scheduling problem, helps to reduce space-time costs when designing fault-tolerant devices. The second one is that, again, as I just showed, transpilation reduces the parallelization of a quantum circuit, but it can also significantly reduces the expected runtime, which in the end may be something interesting for depending on the application. Before I conclude the presentation, I just want to mention that we at 1QBit implemented these two algorithms, the transpilation and the scheduling algorithms, and they are part of our software toolkit that we call as TOPCAD, which stands for Topological Quantum Architecture Design. And we hope that this toolkit in the end can assist researchers and businesses in the design of fault-tolerant quantum architectures. Just to mention, like the scheduler is here, and the transpilation would be on the circuit optimizer part. And yeah, it worked. So this is a short video because I just want to show you guys that. Yeah. So in this toolkit, whoops. Yeah. Anyway. Yeah, it's working, good. In this toolkit, the user can input a circuit a target error bound, for example, 1% as the probability of maximum allowed probability of error for running that circuit, and the parameters that characterize a qubit, such as like the running time, like the measurement time, the qubit fidelity, and so on. And our toolkit run a bunch of tools, including the scheduler and the transpiler, that optimizes the circuit to given a suggested fault-tolerant architecture, meeting the conditions that were informed, generating a resources estimate for the scenario path. So I'm not sure if I can return here the video, but in the beginning, I showed that here you can see that we have like the expected runtime, the number of physical qubits, and then the rest is a report showing like where these qubits are, for example, the fidelities of the logical qubits and so on. So we are currently working on rounding some corners before releasing TopCAD publicly. So we will release more information about it soon. If you are interested to know more about its capabilities or have any question about the tools that I presented, feel free to contact myself. Yeah, thank you very much for listening to my presentation.
Yeah, questions?
Hi, thanks for the nice talk. It was a bit of a basic question. The last table you showed comparing pre and post transpiled. So that was like averaged over the use cases you showed before.
Yeah.
Is post transpiled better in all cases, or is there maybe some reason to?
No, it's pre and post for the average for like all the circuits. I have a.
Yeah. So that on average, it's.
Yes, it's on average.
But in all cases, is it better? Or is there maybe some reason to...
In all cases, it's better. So this is what I mentioned at the end of the slide. So this is what I say here. In all cases, the lower bound for the pre-transpiled circuit is worse than the upper bound for the post-transpiled circuit. So regardless, for the circuits that we tested, for the set of circuits that we tested, regardless of like parallelizing operations or not, we can achieve like fewer logical cycles for the post-transpiled circuit than optimizing everything as possible, like parallelizing everything as possible in the pre-transpiled circuit. This is the main takeaway here.
All right, fantastic. Thank you.
Thank you for the very interesting talk. I saw, like in the earlier half of the presentation, you had these Y magic states, right, for implementing the pi/4 rotations. Is that correct? So those would be the pink rectangles. But then later in the presentation, you used this transpilation pass to remove the pi/4 rotations.
Yeah.
So do you still require pi/4, like these Y magic states, or not in the end?
Yeah, in the end, if we remove all the pi/4s, these pink rectangles are removed, so we do not need them because we do not need like any zero states. I'm just showing here because, again, for the experiments we run pre-transpiled circuits, so we need them.
I see. For the pre-transpiled ones, you do still need them.
Yeah.
Right, but when you're implementing a like multi-qubit poly measurement that includes Y support, even if it's a pi/8 rotation, you know, those are not necessarily native in lattice surgery, right? So. Like for example,
do you mean a case like this, that we have like
there,
Y?
exactly, it has Y support there. Doesn't that also require some sort of Y magic somewhere, or is it possible to implement that with lattice surgery?
No, actually the magic states only require Z connections to the data qubit, so Y is not necessary for the magic state.
Very interesting. Maybe you can explain that to me later. I also had a more open question. So here you were very interested in routing, like positioning like how to use a bus, right? But did you also consider how to best position the qubits within the data blocks in order to minimize routing, or?
Yes. In our full algorithm, let's say like that, we also have like a matching, let's say like an assignment problem to decide like which data qubits should be used compared to this one. So in this example here, I just wanted to keep it simple. I'm using like 1 as this one here, 2 as this one here. But of course, like we need to solve like this assignment problem if we want to actually optimize the whole thing. So yeah.
Is that part of your architecture? Does that paper show how your paper show how to do that, or?
In this paper, we just use it like random assignments, so we do not explore that. But in our software, we have like a more optimized way to assign the qubits.
Fantastic. Yeah, I'd love to see how you guys approach that problem.
Okay, thank you.
Hello, here. Thank you for a great talk. So for the transpilation thing, I wonder what is the pre-transpilation circuit that you're trying to run, and is it optimized in any way? Or?
Yeah, that's a very good question, actually. Let me think I have it. Yeah, okay, I think I can start from here. So as I mentioned, like for this architecture, of course, we need like these operations to be on the as poly measurements. But of course, like circuits can have like different types of, gate set, can be represented by different gate sets, can have like arbitrary angles and all this stuff. So in this paper here, we do not explore that. But in our software, we have a decomposer step that we use to actually optimize the circuit before the before the transpilation algorithm, in order to convert first, like remove the arbitrary angle gates using, for example, Solovay-Kitaev method to transform, these arbitrary angles into the Clifford plus T gate set, and also to convert these operations here into the Clifford plus T to the poly rotations measurement. So the whole pipeline does not start in the transpilation method. I just want to make this very clear. We have like steps where we optimize the circuit until we get to that point.
Okay, and maybe a small follow-up question. So in the table you present, I did not see like a comparison for the T depth. So you only compare the circuit depth. So do you have an idea of the T depth comparison?
Yes, let me get there. Yes, T depth is here, actually on pi 8 operations. Because again,
So this is steps, this is not number.
Oh, sorry, yeah.
This is number, right?
Yeah, okay, good question. I just remember. We have in the paper, I don't have like in this table the exact number, but you can see, like you could do the math by comparing this depth, the length here, and with the average width. So that, if you divide one by the other, that would give you the final depth for the circuit.
Okay, thank you.
Thank you.
Okay, no other questions? If not, let's thank all the speakers again.
Okay, so welcome to the late morning session. And the first speaker will be Chunhao Wang from Penn State University, and he's going to tell us about efficient optimal control for open quantum systems.
Thanks. So, welcome back. Okay, so this is about efficient optimal control for open quantum systems. So you might wonder, what is an open quantum system? So I will start telling you what is a quantum system, or I will start with the very simple model, a closed quantum system. So a system is just an abstraction of quantum device, which evolves on its own. In other words, if you have an initial state, then after a certain time, t, it will evolve to a final state like this, okay? And the word closed, it means there's no interaction with the environment. So the system just evolves on its own. So if in this case, the dynamics of the system can be modeled by a differential equation called Schrödinger equation. So this H is Hermitian matrix, it's called Hamiltonian. And this evolution is also called Hamiltonian evolution. This psi is the state vector, and the solution to this Schrödinger equation is this. So this, if H is Hermitian, this e to the minus iht is a unitary operator. So there is a closely related problem to this optimal control problem. It's called the Hamiltonian simulation problem. So if you wonder what is the output state for the system, you just implement this unitary operator e to the minus iht by designing the circuit to mimic the behavior of this unitary. So we need the output of the circuit to be close to the desired state. So this is the Hamiltonian simulation problem. So once you can simulate Hamiltonian, then we ask, how can we control this Hamiltonian to get some desired state? So this comes to the optimal control problem for closed systems. So again, this is closed system. And by controlling, we want to have some access to the external control field to control the dynamics of the system. For example, you can shoot a laser beam on the system. And imagine that you have a dial for the laser beam, which where you can adjust the power of the laser. Then this power is determined by this function u of t, this continuous function. And this mu is Hermitian operator corresponding to the external control field. Then with this field, the control field, the system, the Schrödinger equation becomes time dependent. So this H is corresponding to the fixed Hamiltonian. This u of t times mu is the control field. And the solution to this time dependent Hamiltonian evolution is slightly more complicated than just e to the minus iht. So here this becomes integral, and you also have this time order operator to control the order of the integral. And then for the optimal control problem, the objective is to determine a control function u of t so that this objective value is maximized with respect to this observable O. So how can you determine this control variable so that this maximized, it is called the optimal control problem. And you can imagine that it is a very important problem. It has many applications, and there are a lot of classical algorithms for solving this problem. So, but the classical algorithm also suffer from the exponential growth of the resources in terms of the number of qubits. So we have quantum algorithms for solving this optimal control problem. And we define this objective function, which is this expectation value, but we also have this regulator term. So recall that we want to maximize this objective function. So we have this regulator term to make sure the control function is not too large. Then the technical ingredient for this optimal control algorithm is quite simple. So it's just the first, you need to run this forward pass, which is the time-dependent Hamiltonian simulation. You can apply your favorite time-dependent Hamiltonian simulation algorithm to simulate this time-dependent Hamiltonian. Then the backward path is to you apply your favorite quantum gradient estimation algorithm to estimate the gradient of this objective function. Then once you have the gradient, you can do gradient-based classical optimization, which will optimize this objective function by iterations. Okay. So this is classical. So this is the optimal control for closed systems, and the previous results shows that this can be done with the query complexity t squared over epsilon cubed. Now we know how to control closed system. Let's talk about this open system. All right. Okay. So this is the picture of the closed system, and you can see that there's no interaction with the environment. But if there is interaction with the environment, the system is open. Okay. So this closed system or Hamiltonian evolution only exists in textbooks, but in reality, all the systems are more or less interacting with the environment. So if you believe the whole universe is a unitary process, then every subsystem is interacting with the environment. So it's not perfect. So this open system is actually the correct model for modeling this real life quantum systems. And there are many regimes for this open quantum system. So if this interaction is not too strong and the environment refreshes quickly, then this type of open system is called Markovian open system, in the sense that the information only flows from the system to the environment, but it never flows back to the system. So this Markovian open system. For such systems, we have a nice generator. We use this master equation called Lindblad equation to describe the dynamics of the system. So this L, script L is a super operator. It has two parts. The first is the Hamiltonian part, and the rest is the dissipation part. So again, this H is Hermitian, but there's no restrictions for this LJs. So they can be any operator. And these LJs are called jump operators. And this super operator maps matrices to matrices. And the open system will produce a mixed state, which is an ensemble of pure states. And this L is called the Lindbladian. And then the solution to the system, to this Lindblad equation is this. So we have e to the LT. So there's no I here. So e to the LT. So if L is in this form, then it's the e to the LT is a quantum channel, which is completely positive, truth preserving. So in this sense, a Lindblad equation generates a quantum channel. Okay. So again, in this case, we want to control an open system. So we just, again, we have this external control field, U of t times mu, controlling this Hamiltonian part. So in this simplified model, and this is the realistic model, we assume we're only controlling the Hamiltonian part, and we don't touch this interaction part. Now, this Lindbladian becomes time dependent. So here, instead of H, we have H of t, this time dependent Hamiltonian. But for the rest of the terms, for the jump terms, dissipation part is time independent. Okay. Then the final state is slightly more complicated. So the final state is this. Again, we have the integral in the exponent, and we also have the time ordering operator. And then the objective for the optimal control problem is to determine the control variable so that this objective function is maximized. So this trace is just the generalization of expectation value in the sense of in terms of mixed states. Okay. And we also have the regulation term to make sure the control function is not too large. So there's a lot of applications for the optimal control in both closed systems and open systems. For example, you can use it to maximize the electric current in electron transport. And you can use it to implement molecular switches. And you can also use optimal control to design quantum devices. So you might wonder, this doesn't make sense, because to implement this this optimal control algorithm, you need fault-tolerant quantum computers. Okay? So how we don't have fault-tolerant quantum computers. How can we use it to design quantum devices? So there is an analogy in classical world. So imagine, okay, so you know that there are a lot of softwares that can help us to design CPU chips, right? So we have classical algorithms to help us design classical machines. So we can imagine that in the future, once we have fault-tolerant quantum computers, we can also use fault-tolerant quantum computers to help us accelerate the process of designing quantum computers. So this is a valid and appealing application for optimal control, and why we studied quantum algorithm for the optimal control problem. And the technical overview for this optimal control problem for open systems is quite similar to this closed systems. So again, we have this forward path, which is simulating time-dependent Lindblad evolution instead of time-dependent Hamiltonian evolution. And then the backward path is again to estimate the gradient of this object function. And then we use this classical optimization, which is called perturbed accelerated gradient descent, to optimize this object function by iterating the two passes. So this perturbed accelerated gradient descent, so it's different from gradient descent because it's we only have estimations of the gradient. We don't have exact gradient. So we don't have the exact gradient, and also because the object function is non-convex, and for this accelerated gradient descent, we only perturb the gradient in some cases, and also when we do the optimization, we exploit the negative curvature to jump out of the saddle point. So this is this is different from standard gradient descent. And then let me first talk about the first pass, the simulating time-dependent Lindblad evolution. So the simulation of time-dependent Lindblad evolution is based on this time-independent Lindblad evolution, Lindblad simulation. So I will explain this time-independent case, and then I will show how to generalize this to time-dependent case. So for this Lindbladian, we can decompose it into two parts. This L sub D is called the drift part, and L sub J is called the jump part. So this is drift. The J is this. So it's quite similar to Hamiltonian evolution, but you have this non-Hermitian part. And this decomposition can be interpreted in some unraveling stories. Then once you have this decomposition, you can apply Duhamel's principle repeatedly. So the Duhamel principle is just a mathematical tool for solving differential equations, and you just so you use Duhamel's principle to treat the two terms differently, and you keep applying this, and then you arrive at the Scherer equation. So, but let me tell you the intuition of the Scherer notation, so that it's not that scary. First, you can just ignore this line. You can ignore the last term. So this, because it's just this is just the integration. This is the higher order integration. It's just the volume of the very tiny corner of the higher dimensional cube, right? So when the dimension is large, this volume is quite small, so you can just ignore this safely. And then for the second term, okay, so let's first look at the integrand. Let's look at this e to the LD. So because LD looks like this, so this e to the LD, it is a completed positive map. And this LJ, this composition, e to the LD composed by this LJ is already completely positive. So the composition is completely positive. So you can see that all the integrand, if you think of the composition of all the terms, so this entire integrand is completely positive. Which is nice. Then you need to deal with this integral, and you can actually use another mathematical tool called the Gaussian quadrature to approximate this integral by a summation. Then this becomes a summation, now it looks familiar, right? It's just in this form, in this completely positive form. So yeah, K. Sorry, K is the K is that controls the how precise this. This is the equality because this you have this this is the error. You basically you drop the last term. So when K is getting larger and larger, the last term is smaller and smaller. So basically K is some polylog term. Yes, the last term is there. You don't care about the last term. It's because it's small. When K is larger, the last term is small. Yeah. So this term is nice because we have technical tools to implement this term. For example, when you are given the block encoding of each cross operator, then you know how to implement this complete positive map by using the result from previous work. Then you can use this to implement this this completely positive map. Then you can simulate this time-independent Lindblad evolution. And the previous work shows that this, the complexity for the simulation is T times polylog T over epsilon. So this is a time-independent case. And we can generalize this to a time-dependent case. So again, we use this decomposition, but now this drift term depends on time. Okay, so because H depends on time. And then we can use, we can still apply Duhamel's principle, but it is slightly different, where you have this script K square bracket something. This means this means this is the cross operator. This is the map where the cross operator is A. So basically, this means this is the quantum completely positive map where the cross operator is this. And then again, this integrand is completely positive. But now this V of ST is like, it looks like the time-dependent Hamiltonian evolution, but you have this non-Hermitian part over there. But you can still use the algorithm for time-dependent Hamiltonian evolution to implement this this operator. Whereas, for example, you can use the algorithms by Kieferova, Scherer, Berry for based on the truncated Dyson series, or the algorithm by Low and Webb based on interaction picture to simulate this map. Then then everything's still in the completely positive form. Then you can use previous techniques to implement this map. But a little bit of technical stuff to note that you can no longer use Gaussian quadrature to approximate this integral in this case, because to use Gaussian quadrature, you need to bound the higher order derivative of the integrand. But in this case, in time-dependent case, we don't know how to bound the higher order derivative. So we can just use this Riemann sum to approximate the integral. It's slightly less efficient. And then again, the time complexity, our query complexity is roughly the same with the time-independent case. So it's still linear in T and the polylog in 1 over epsilon. Now we know how to simulate. We know how to implement the first pass, the time-dependent Lindblad simulation. Now let's get to the second pass, the estimating gradient of the cost function. So the goal is to determine the cost, the control variable U of T, right? But this is a continuous domain. So, but we can discretize the time into many time steps. So we can turn the problem into a finite dimensional problem. So we just need to determine the function value and discretize time steps. Then we can approximate the function U of T. And then by the simulation algorithm, we can obtain the final state rho of T. Okay, but recall that the simulation algorithm is a unitary operator. When you trace out the ancillary qubits, you have this mixed state. But if you don't trace out the ancillary qubits, you have a purification of the target state. Once you have the purification, you can turn this trace into an expected value in a larger space. So again, we have this nice form of objective function. Then we can use the gradient estimation algorithm to estimate the gradient. The gradient estimation algorithm requires a phase oracle, which means you compute the function value in exponent in the exponent of the phase. So, but this phase oracle can be simulated by a probability oracle. A probability oracle means that you compute the function in the amplitude. Okay? And further, the probability oracle can be simulated by this simulation algorithm plus a Tandemar test circuit. So this conversion can be easily done from the simulation algorithm to the phase oracle. Then you can use your favorite gradient estimation algorithm to simulate this, to estimate the gradient. So in this case, we use the quantum gradient estimation by Gideon, Aruna Shalam, and Webb to estimate the gradient. So the result says with high probability, you can output an estimate of the gradient, which is precise in terms of the two norm errors, and the query's complexity is T over epsilon to the gradient oracle, and which means the query to this Link-Blandian oracle is T squared over epsilon. Okay. Then it comes to this classical optimization. You use perturbed accelerated gradient descent. The classical result says the number of iterations is in this number 1 over epsilon to 7 over 4. And then recall that estimating the gradient needs this many queries. This epsilon g is the quality of this gradient estimation. Then the total cost is like this. If you are satisfied with the first order stationary point, then you can choose this quality of gradient estimation to be this. Then the total cost is just the T squared over epsilon to the 23 over 8, slightly less than epsilon cubed. And if you need this second order stationary point, meaning that you also need the second order of the difference to be small, then you need much better precision for the gradient estimation. So this epsilon g is much better than this epsilon, and then the first order case. It turns out that the total cost is slightly larger than this first order stationary case. So this is the result of this optimal control algorithm for open systems. And there are open questions. The first open question is, can we get simpler algorithm for time-dependent Link-Bland evolution? So recall that for the time-independent case, we have a simple algorithm where everything can be turned into a completely positive form, and we just use Gaussian quadrature to approximate the integral. And I told you that for this time-dependent case, we don't know how to apply Gaussian quadrature. So you need extra steps to take care of the time ordering. If you use Gaussian quadrature, you don't need to take care of the time ordering. But here, you need to actual techniques to take care of the time ordering. For example, you need this quantum sort or compression scheme to handle this time ordering. So this is more complicated. So we wonder if we can get a simpler algorithm for time-dependent simulation algorithm. And then can we get the optimal control problem beyond the Link-Bland case? The Link-Bland evolution is corresponding to the Markovian open system. But when the interaction is much stronger, this is no longer Markovian. Okay? So can we still get optimal control for this non-Markovian open systems? And the last question is, can we work this out in a different cost function? So the presented cost function is to estimate to maximize the the expectation value, right? But what if you just want a specific target state, and then the objective function can be the trace distance between your final state and the target state? Then if you can estimate the gradient of this objective function, then you can solve this optimal control problem. So I think that's all I want to say, and thank you so much for your attention.
Thank you. Are there any questions?
Thank you for your talk. So I'm wondering if for the time-dependent Lindbladian case, if the Lindbladian at different time commute with each other, so can we still use the simpler simulation algorithm?
Oh, this is a good question. I think I forgot the why exactly we cannot use Gaussian quadrature. If commute possible, but I have to double check.
Because if commute, there's no time ordering issue. Right?
Oh, well, yes. If there's no time ordering, then everything is much simpler. Yes.
Okay, thank you.
Thanks. And if it's commute, we just use trotter, right? Yeah.
Any more questions?
Yes, thank you for the talk. So in the time-dependent or maybe independent even evolution, so you have this integral to estimate.
Yeah.
But is it true that this integral is high dimensional, right? So K is large.
K is large. Yes, yes, yes.
Right, so but if you estimate a high dimensional integral by discretization, you incur the cost of dimensionality, right? So basically you need to have a lot of points to sample, right? So this grid basically becomes very, very large. So isn't this a problem?
Yeah, this is a good question. So actually you can, the grid point, if you implement the circuit, it's nested. You can use nested techniques to prepare the initial state of the controlling register. So it's not a problem. It's only the complexity depends on K. So it's not you don't have a curse of dimensionality here.
Any more questions? Okay, so let's thank the speaker once again.
Thank you.
Okay, so next speaker is Josh Cudby from Cambridge, and he's going to tell us about Gaussian decomposition of magic states for matchgate computation.
Okay, hi everyone. First of all, just thank you to the conference organizers for putting on such a great conference. So yeah, today I'm going to be talking about Gaussian decomposition of magic states for matchgate computations. And this was joint work done with my supervisor, Sergii Strelchuk. Okay, so just to give a quick outline of what I'll talk about today. We're going to start with some background and motivation. So I'll talk a little bit about classical simulation of Clifford circuits, and then I'll give some background on what matchgate circuits are and matchgate computations. I'll then talk about Gaussian states. So I'll give some definitions. I'll then talk about algebraic constraints on Gaussian states, and I'll talk quickly about the Gaussian fidelity. And then finally, I'll talk a little bit about matchgate circuit simulation, and in particular, the Gaussian rank. So let's get started. So what do I mean by classical simulation of quantum circuits? So traditionally, we've got two types of simulation. We have weak simulation, which are algorithms which take a description of a circuit and samples from the output distribution. And we have strong simulation, where we have algorithms that take a description of a circuit and compute any desired output probability or marginal output probability. And as you might expect, strong simulation implies weak simulation. So for the purpose of this talk, we're just gonna assume simulation means strong simulation. Okay, so what are Clifford circuits? So the Clifford group is the set of gates which preserve the Pauli group under conjugation, and they're explicitly generated by the Hadamard gate, the C0 gate, and the phase gate S. And we have this very celebrated theorem that if you have a quantum circuit which acts on a computational basis state, consists only of possibly adaptive Clifford gates, and contains measurements only in the computational basis, then that quantum process is classically, efficiently, strongly simulable. And just for some notation, we call states prepared by Clifford circuits stabilizer states. So since Clifford circuits are classically simulable, they don't achieve universal quantum computing, but we can extend them to a more powerful gate set in a couple of different ways. The kind of most obvious way is to give them access to a new gate. So for example, the T gate, which I've defined up there, it's the square root of the phase gate S. Then the gate set Clifford plus T is actually universal. But instead, we can actually give them access to a different resource. We can give them access to so-called magic states. So if we define this state A, which looks kind of like a T gate in some sense, we actually have this small Clifford subroutine which consumes a copy of a magic state A to implement a phase gate T. So how do we do that? We take the line we actually want to put our T gate on, and we take one copy of an ancilla, we apply a C0, we take a measurement in the computational basis, and then we do this correction operator dependent on the outcome of this measurement. And if you go through and actually check that, you can see that this exactly implements a T gate. And since having access to these states A boosts the power of Clifford gates to a universal set, somehow magically, they're known as magic states for Clifford circuits. Now, how does this relate to classical simulation? So here's a simulation algorithm based on this idea. We first express any quantum process you like in terms of a Clifford plus T circuit. Then we gadgetize the circuit. So we replace all the T gates with those small subroutines I showed earlier. And the result of doing that is some circuit C acting on still n copies of the zero ket, but now also k copies of the magic state, where k is the number of T gates in the gadgetized circuit. Now we can imagine expressing this k copies of the magic state in terms of a big sum of k-qubit stabilizer states. Now for each term in this decomposition, if we consider them separately, the quantum process is now a Clifford circuit C acting on a stabilizer state. And by the Gaussian-McNeill theorem, which I showed earlier, this is efficiently simulable. Now, of course, there's no such thing as a free lunch. We've not just solved simulating quantum processes in polytime. So what is the complexity of this? So the complexity is dominated by the number of terms in the decomposition. So we call the number of terms the stabilizer rank. It's given by this expression chi here, and it's the minimum possible number of terms in any such decomposition. And since we expect simulating quantum processes to be exponentially hard, we expect that T should scale like 2 to the alpha k for some constant alpha. Now, if you just do this naively in the computational basis, we'll have 2 to the k terms, so alpha equals 1. But actually, if you do something more clever, the kind of best known decomposition, at least best known to me, gives alpha something like 0.4. So there's actually really tangible benefits to finding better decompositions for doing these simulations. Yeah, so this alpha 1 is made by combining these like cat states together. It's quite non-trivial, but it does end up with quite a good decomposition. Okay, so I'm now going to change tack completely and give some background on match gates and match gate circuits. So a match gate is this rather strange looking 2-qubit gate. It's got 2 parts. It's got an A and a B, and A acts on the even parity subspace, so the 0, 0 and the 1, 1, and B acts on the odd parity subspace, so the 0, 1 and the 1, 0 gets. And A and B both have to be unitary, and crucially, they have to have the same determinant. Now, circuits of nearest neighbor match gates are known as matchgate circuits, and actually, nearest neighbor is really important here. You can check that the swap gate is not actually a match gate because the determinants don't match up. So giving access to swap gates is actually giving these circuits more power. So we enforce nearest neighbor. Now, matchgate circuits are efficiently classically simulable. And in some sense, this is because they're very closely linked to the theory of non-interacting fermions, which is a solvable physical model. And I actually think this is really interesting because in some sense, Clifford group is a really nice mathematical structure, but it's not that well physically motivated, whereas matchgate circuits are kind of directly physically relevant theory. So just to kind of delve into that a little bit more, if we have a system of n free fermions, we associate with them these creation operators, A1 dagger to AN dagger. But actually, mathematically, it's much easier to work with two n operators called the Majorana operators, and they're defined up here. There's a kind of odd one and an even one, which is slightly different. And the gamma mu are chosen to be Hermitian, square to the identity, and mutually anti-commute. And just to put some like concreteness on this, one particular representation of them is the so-called Jordan-Wigner representation, in which they're just these very simple Pauli strings of a bunch of z's, and then either an x for the odd case or a y for the even case. And just to kind of show the link between matchgate circuits and these Majorana operators, matchgate circuits actually act as rotations on the Majoranas. So when we conjugate a Majorana by a matchgate circuit, we end up with this action over here, where Q is a special orthogonal matrix. So traditionally, this is how people have worked with matchgates in terms of kind of the action on the Majoranas. Now, once again, we can extend matchgate circuits to a universal set. And I actually mentioned this earlier, that the swap gate gave matchgate circuits more power, and it actually turns out that it gives them sufficient power to be universal. And once again, we have a small subroutine, which instead of giving them a swap gate, we can use this subroutine and a certain magic state to perform a swap gate. Now, it's not quite as nice as the Clifford one, so I'm just going to flash it, but don't feel the need to kind of pass the circuit too much. But you can go in and check that this is, in fact, an adaptive matchgate circuit. Now, what is the magic state that we care about? For us, we're going to take this very simple state. It's just a 4-qubit GHZ state. And I'll actually check that it's magic later, but you have to take me at my word for now. Okay, so that gives some kind of background and motivation. So let's talk a little bit now about Gaussian states. So a Gaussian state is defined to be a state which is prepared by a matchgate circuit acting on the zero ket. And it's actually known that any state of fixed parity, so only contains computational basis states with an even number of ones, say, any non-Gaussian state of fixed parity is known to be magic for matchgate circuits, which is quite a powerful result. And we also have this classification of Gaussian states given by Sergii Bravi. And we take 2 copies of each Majorana operator and tensor them, sum over all the Majoranas, and act on 2 copies of a state. And a state is Gaussian if and only if the resulting expression is 0. Now, equation 1 is quite a nice kind of compact representation, but it's not very useful to actually get a grip on what these Gaussian states look like. So we can expand equation 1 in a computational basis to get a sort of explicit set of algebraic constraints. And these explicit constraints are super useful to actually get a better handle on the manifold of the states and do all our later work. But warning, the equation looks a little bit scary. So what happens? We end up with this big mess where we have a sum over odd weight strings. And then inside that, we have a sum over the length of the string or the number of qubits, and we have this nasty looking expression. But actually, it's not that scary. We have, as I said, one constraint per odd weight pair, and each equation has a term for each bit I where xi does not equal yi. And actually, if the Hamming distance between the two strings is less than or equal to 2, the constraint is trivially satisfied. So, for example, if you only have 4 qubits, it actually turns out there's only a single constraint, and it looks like this. So I flipped between binary and decimal here, just because I didn't want to write out loads of binary strings, so forgive me for that. But it's actually not too scary. It's just this alternating sum of quadratic terms. So why are we interested in this? So the manifold of just all even weight states is just parameterized by all these variables a mu. It's very simple. Whereas the manifold of Gaussian states so far is parameterized by all these complicated constraints. We have loads of them. But ignoring duplication, there's this like sort of nasty combinatorial number of non-trivial constraints. And actually, this is too many constraints. If they were all independent, we wouldn't have any Gaussian states. But we know that it is possible to prepare states with matchgate circuits. So clearly, not all these equations are independent. Now, how are we going to find an independent set? I'm going to appeal to something called the implicit function theorem. And if you've not seen this before, all you really have to care about is that it essentially says that imposing m independent constraints removes n degrees of freedom. And if you want a slightly more technical version, essentially we have m functions on m plus n variables. So we partition our variables into 2 sets. And if the Jacobian of the functions with respect to the first set of variables is non-zero at some point, then there is some solution of the w's in terms of the z's. So essentially, the w's become dependent variables and the z's remain independent variables. Now, how do we apply that in our case? So we have this large set of functions, f, indexed by the odd weight strings xy. We partition the variables into w, which is the set indexed by heavy weight strings, and z, which is the set indexed by low weight strings. And we now need to find a set of m functions that we think are independent. And how do we do that? For each w, which is heavyweight, we find its first one, and then we take the constraint function fxy equals 0, where x is just a single one in that first bit, and y is the string w, but with its first bit kind of unset and changed to a 0. And if you actually go through and do the calculations, you can end up seeing that the Jacobian is block upper triangular, and the blocks along the diagonal are just multiples of the identity. So in particular, the IFT holds, and we have an independent set of constraints. It's sort of for any amplitude which is non-zero, you can pick a set around that one. So you kind of have this like patched local version to get it globally. It's a little bit technical, so I'm not going to go into it here. So what can we do now that we have this kind of explicit and small description of Gaussian states? So one thing we can prove is that the Gaussian fidelity is generally exponentially small. Now, what's the Gaussian fidelity? It's very simple. It's just the maximum overlap of the state you care about with any Gaussian state phi. Now, so yeah, for a Haar random state, we can show that the probability of having non-negligible overlap is actually exponentially small. And just to sketch the proof, we use the constraints that we found, the independent set, to construct an epsilon net with size not too bad, essentially. Now, 2 to the poly n kind of looks bad, but it all shakes out in the end. And then we use properties of the Haar measure, and we take a union bound over that net to show that with high probability, the fidelity of any state on the net is exponentially small. And then the fidelity of any general Gaussian state, not necessarily on the net, is only a constant factor larger with high probability. Okay, so now I'm going to switch over to my final section and the kind of whole purpose of this project, which was to try and look into matchgate circuit simulation. So first of all, how do we do matchgate circuit simulation? Well, it's very similar to the Clifford case. We take any quantum process we like, and we can write it as a matchgate plus swap circuit. So that should not be a T. Then we can gadgetize that circuit to obtain an adaptive matchgate circuit acting on n copies of the zero ket and k copies of this magic state M, which remember is on 4 qubits. We can then decompose M into Gaussian states. And for each term in this decomposition, the quantum process is a matchgate circuit acting on a Gaussian state. So for very similar reasons to earlier, this is classically simulable. So this is an algorithm for simulation. And once again, it's dominated by the number of terms in the decomposition. So we define analogously to the Clifford case, the Gaussian rank, and it's just the minimum possible number of terms in a decomposition into Gaussian states. So in our work, we investigated k equals 2 and k equals 3 to try and find some low rank decompositions. Now, actually, already it's quite computationally expensive to work with only 2 and 3 copies because that's 8 and 12 qubits. And when the sort of pioneering work was being done in the Clifford case, they found that going beyond 6 or 7 qubits was very hard to optimize over, and we kind of experienced similar difficulties. So what did we manage to do? On the analytical side, we noted that 2 copies of the magic state is invariant under a pair of Z operators on either the first 2 or last 2 qubits. And now if we impose that same condition on the Gaussian states in the decomposition, we can actually make some progress. And essentially it's because all the constraints that we defined earlier that we saw, we saw one that had 4 terms in, they actually all collapsed to only having 2 terms. And we can do a very long and extensive case bash and it's proved that there are no low rank decompositions for symmetry restricted Gaussians. Now, we don't really claim that this is necessarily convincing evidence that there is no low rank decomposition for k equals 2, but it does show that any decomposition will have to be, at the very least, kind of non-symmetric and maybe surprising form. And on the numerical side, we ran loads of simulations and loads of optimizations over like many thousands of computer hours, and we didn't find anything. So we conjecture that there are no low rank decompositions for k equals 2 or 3. Now, we kind of view this as a challenge to the community. It's well known that the best way to get an answer to a question is to post a wrong answer on the internet. So please do go ahead and find some low rank decompositions. We'd love to be proven wrong. And the kind of conclusion of all this is that any rank-based simulation method for matchgate circuits depends on low rank decompositions by its very nature. And these are hard to find. So just to give a quick summary, we give the first explicit algebraic constraints obeyed by Gaussian states. We then use those to, for example, prove that the Gaussian fidelity is generally small. And we initiate a study of the Gaussian rank that essentially only give negative results in that area. And looking forwards, I think it's pretty clear what the outlook is. We really want to find low rank decompositions of fermionic magic states. And if that's not possible, maybe we can prove lower bounds for the sort of non-restricted case or on the rank on a few copies of a fermionic magic state. Thanks very much for your attention.
Okay, any questions?
Thank you for the very nice talk. It's a very tricky problem.
Yeah.
Here you looked into, magic states for implementing swap, right, as a tool for achieving universality in this model. But since matchgate circuits are like inspired by like non-interacting fermions, right? It's really equivalent to that. You could take different routes to achieving universality, different ways of generalizing the dynamics to like say weakly interacting fermions or something. Have you looked at, trying to achieve low rank decompositions of other types of magic in the swap gate?
Yeah, it's a really good question. And I think magic in the matchgate case is kind of a lot more subtle than in the Clifford case, because it's not the case that it's either magic or not. There's definitely this kind of continuous spectrum. And I don't think there's been enough sort of studies yet on, we have all these magic monotones in the Clifford case. So it would be really interesting to try and see if maybe swap gates aren't the way forward. I do think once you've translated into the computational like qubit model, since match gates plus swap are universal, you could always express any other bonus gate you were giving them in terms of match gates and swaps and get back to this. But it's definitely possible that the kind of decompositions would be more visible in that other setting. So I think it's definitely something that could be looked into.
Very interesting. Thank you.
Hi, this might be a very basic question about match gates, but like with Clifford gates, I can think of like the Hadamard, the C-naught, and the phase as generating this whole structure. Is there a similar set of like gates, maybe parameterized gates I can think of as generating the match gate?
Yeah, so there are sort of finite generating sets, and there's a certain model of computation called fermionic parity-based computation, which explicitly depends on this like finite generating set. It requires a kind of characterization of Gaussian of match gates I didn't actually give in this talk because we didn't really need it. But you can parameterize them by quadratic Hamiltonians in Majorana operators. And it turns out that you only need pi by 4 as a phase in your quadratic Hamiltonians, and that actually generates the whole set. So it's not quite as easy to write down like a nice kind of 3 or 4 gates, but there is a finite generating set.
Well, thank you.
No problem.
Any more questions? Can I ask? So you didn't find a low decomposition, right? But you do have the natural decomposition. Does give you something, right?
Yes.
So is it better than Clifford plus T in some circumstances? I mean, that if you want to simulate something which is almost completely.
Yeah. So I think there are certain hardwares out there that are kind of native to match gates. So, for example, like Google's 2-qubit entangling gate is a match gate. So you could definitely argue that actually match gates would be the route to go to for simulation rather than translating it into the Clifford picture.
Did people ever try it as a practical tool to simulate?
Yeah, so actually at the same time as our paper came out, 2 papers very similar, kind of on the more practical aspect of actually doing the simulations came out. And I think they reported like quite positive results on actually doing the simulations, whereas we are more interested on the kind of the quantity that controls the cost of it. But there are some applied results, yeah.
Any more questions? Okay, so thanks the speaker once again. Okay, so the last speaker for this session is Blake Holman, and he's going to tell us about parallel reversible pebbling, quantum circuits with low amortized space-time complexity.
Thank you. Yeah, I'm Blake, and I'm going to introduce the parallel reversible pebbling game, and then I'll show you how to use the game to construct quantum circuits that are efficient for a variety of problems. So we're interested in time-space trade-offs. When you're designing an algorithm to, say, compute a function, oftentimes there are many ways to manage your space and time resources. You could have one algorithm that when we look at the space usage over time, it uses relatively a large amount of space, but it gets done with the computation relatively quickly. You could also design an algorithm that's space-bounded at the cost of a longer runtime. On one hand, qubits are expensive, so it's advantageous to be space efficient. On the other hand, we could be too extreme in our attempt to save space, and even if the problem is still computable, the runtime could be too long so that it's infeasible. It also can lead to more decoherence. And that's why we are studying amortized space-time complexity, which quantifies how good of a trade-off our algorithm does. In particular, amortized space-time complexity measures the total amount of space used across all of the time steps. Equivalently, it's the average space usage times the runtime. So if we have an algorithm for some function f, and we examine the graph of space usage over time, amortized space-time complexity is just the area under the curve. So we're actually interested in a harder problem, which is coherently evaluating functions, that is, evaluating them in superposition. And this is a common task that we need to do because for a lot of the cool quantum advantages we want to use, we usually assume black box access to some function. In reality, though, we have to implement those oracles. And it can actually be much more difficult to design an efficient coherent quantum circuit for evaluating the function than it is to, say, design a classical algorithm to evaluate it classically. And this is in part due to the reversibility of quantum computation. So how do we usually get around this? Well, the standard technique is to start with an efficient classical algorithm for computing the function f. And then we design a reversible classical algorithm by replacing every irreversible operation with an equivalent reversible one, essentially keeping around all the information that we would have deleted. And this does work. In fact, it actually maintains the time complexity of the original algorithm. The problem is that it blows up our space usage and thus our amortized space-time complexity. And so in this work, our main result is that we introduce this thing called a parallel reversible pebbling. And then we use it to map irreversible algorithms to reversible ones while maintaining the amortized space-time complexity, except for a small multiplicative overhead. So let's give an example on why the standard technique can fail. Here, we're interested in iterative functions. So we have some function h, and we want to compute h to the n of x, where h to the n is just h composed on itself in times. Designing a classical algorithm that's efficient is pretty easy, because we can just compute the function in place. So we have x, we can compute h of x, and then with h of x, we can compute h of x, and so on, until we're done. But something changes when we want to design our quantum circuit for the problem. In particular, we can't just compute the function in place, because that is not reversible. So usually what we do is we will XOR the value of h into a new register. So we have h of x. But now we're left with the same problem, and we have to do it again. So we have h2 of x. And now we're already using more space than the classical algorithm. but we can go ahead and finish. And then when we're done, because we want this circuit to be coherent, we need to uncompute the intermediate values. Okay, so this takes some more queries, but it's a standard technique, and eventually we can do it. But there's a clear problem in that for the classical algorithm, we had amortized space-time complexity equal to n because the time complexity is linear and the space complexity is constant. But for our quantum algorithm, we see that we have quadratic amortized space-time complexity because both our space usage and our time were linear. And so we looked at this example and saw that the standard technique fails to preserve this complexity metric. In particular, if we're not careful, our reversible algorithm can have much higher amortized space-time complexity than the original. So the question we might ask is whether or not these iterative functions are some special case that we don't really need to worry about, or are they representative of typical problems? And so I'm going to claim that they are representative of typical problems. That's because the standard way of mapping irreversible algorithms to reversible ones essentially treats each irreversible algorithm as an iterative function. So we can kind of map out this line graph that represents the runtime of the irreversible algorithm CF, and each node represents the state of the algorithm at that time step. So at time I, the algorithm transitions to state 2. State 2 takes as input the previous state of the algorithm, and then outputs state 3, and so on, until we get to the end, where the output is the function. So this is an important problem, and it has been studied for a while. In the 80s, Binet introduced the reversible pebbling game, and he shows how to convert irreversible algorithms to reversible ones. The idea is that we generate what's called a reversible pebbling of the line graph. And then using that pebbling, we can actually create our classical reversible algorithm for the problem. And then we know that taking the reversible algorithm and generating the quantum circuit is straightforward. So Binet's pebbling is nice because it preserves space-time complexity, which is the maximum space usage times the time. Not yet. So soon we will learn how to reversibly pebble. So Binet's technique fails to preserve the metric we're interested in, which is the much stronger amortized space-time complexity. And remember, that's just the average space times the time, which is usually a lot different than the maximum space times the time. It also space-time complexity also fails to capture the cost of parallel algorithms, which is important for proving the security of certain cryptographic primitives, as well as for limiting decoherence. So what is the real difference between these two? Well, if we have an algorithm, we know the space-time complexity is the time multiplied by the maximum space usage, which is like the bounding box of our plots of space over time. The problem is that it doesn't work well for parallel algorithms because it doesn't scale. In particular, if I have an algorithm that has high space-time complexity, but the maximum space usage is only used for a short amount of time, I can do something like stagger the start times of our algorithms and then compute the function many times in parallel with a space-time cost that is essentially like computing at once. Therefore, it's not very descriptive, and if you try to set up your system based on your space-time complexity, you could be vastly underutilizing your resources. With amortized space-time complexity, time multiplied by the average space usage, we see that it's the area under the curve, and so the amortized space-time complexity of computing a function 3 times is 3 times the amortized spacetime complexity of computing at once. So the good thing, though, is that we can still analyze amortized spacetime complexity with this tool called the pebbling games. Okay, so what's the reversible pebbling game? Well, in this setup, we have some DAG. In this case, it's a line graph, which represents our iterative function like before. Each node has a label. In this case, the label for node V is just h to the v. And the last label, the label of the last node in the graph corresponds to the output of the function. In this game, we have a set of pebbles, and each pebble represents a chunk of memory. In this way, placing a pebble on a node corresponds to computing the label and storing it. Removing a pebble corresponds to unallocating that memory, so I can use it elsewhere. And in our parallel version of the game, the only difference is that you can place and remove many pebbles at once. Okay, so let's go through a little example. The exact rules of the pebbling game are that at the beginning, so you can always place a pebble on a node whose parents already have pebbles on them. So right here, we can pebble the first node. You can't remove a pebble if it was just used to produce another. That's because you needed that information to generate new information, so you can, at the same time, you cannot undo it. Lastly, we can only remove a pebble from a node if all of its parents have pebbles on them. So this makes sense because if we're trying to uncompute something, then we have to re-query the information in order to remove that label. Okay, so let's go through our old example. First, we computed h of x, and so that's going to be like placing a pebble on node 1. Using h of x, we can place a pebble on node 2. So because we have node 1 pebbled, we can place a pebble on node 2, and so on, until we've finished the computation. So placing a pebble on that last node corresponded to evaluating the function. And then we have to uncompute, which corresponds to removing these pebbles, which we can do simply, and we're done. So that's a reversible pebbling. Okay, great. So let's go through our results. So first, we're going to go through our new parallel reversible line graph pebbling. Then we're going to use that reversible line graph pebbling to generate a transformation from irreversible algorithms to reversible ones while maintaining the amortized space-time complexity. And then we're going to show how we can apply it to generate attacks for a cryptographic primitive called memory hard functions. Okay, so to do our line graph pebbling, we just generalized the original reversible line graph pebbling of Binet. So what we did is we optimized some implicit parameters and then we parallelized it. So how does it do? Well, the time complexity of the naive strategy was linear. Binet's pebbling is slightly more than linear, but we show that by parallelizing it, we can get it back to linear. This corresponds to being able to simulate the irreversible algorithms while maintaining the time complexity. And so our space, we improve a lot on the space complexity. Before it was linear space, and now the space usage is subpolynomial. And we're in our parallel algorithm, we actually use a little bit more space to get our time advantage. So in the end, the amortized space-time complexity is the same for both of them. But you see how we improve from quadratic amortized space-time complexity down to almost linear. We also give a lower bound, so you can't really do much better than this. Okay, so we have a nice linear pebbling that has low amortized space-time complexity. Well, what can we do with it? So on its own, this pebbling does not preserve amortized space-time complexity. That's because each node has a different amount of space associated with it. So what we can do is take our line graph again for the runtime of C, And then we can assign weights to each node corresponding to the space usage at that time step. If we classify nodes as, say, light, medium, and heavy, in reality, there's a lot more than that. Then we can try to design a strategy that has low complexity given these weights. So the space usage at a step in our pebbling is just the sum of the weights of all of the nodes at that time step. What we do is we try to use our old strategy, the new parallel reversible line graph pebbling, but we only want to pebble the light nodes, say 1, 6, and 8, because if we keep pebbles on the heavy nodes, it's going to be expensive and it's going to blow up our amortized space-time complexity. Now, we can't just do that because indeed there are nodes in between. Placing a pebble on node 6 will be illegal, and so we're going to recursively fix all these illegal steps. And the point is that we want to keep pebbles on heavier nodes for as little time as possible, and we can afford to do that because there are relatively few heavy nodes relative to the average space usage of our algorithm. Okay, so let's go through a little example. We want to pebble this graph, and so like I said, we want to pebble only the light nodes, ideally. So we place a pebble on node 1, but then we encounter a problem immediately. To pebble node 6, we have to pebble this whole line graph in between it. So we're just going to call this pebbling strategy again recursively on this subline graph. Okay, again, we just want to pebble the lightest nodes that we can. So we place a pebble on node 2, but now there's another line graph in between. To place a pebble on node 5, we then have to pebble nodes 3 and 4, and pebble node 5. But nodes 3 and 4 are heavy, so we want to keep pebbles on them for as little time as possible. So we're going to go ahead and unpebble them. Okay, now we can pebble node 6. We have to remove the medium pebbles now, which means we have to repebble the heavy nodes and so on. Okay, and then we're able to clear off all of the previous pebbles, and so now we're not using so much space. To finish the pebbling, we just have to do one more recursive call, pebble 7, and we're done. So that's a high-level overview on how we are able to get this transformation, where previously we were not able to preserve amortized space-time complexity, but this strategy does. In particular, we have this small overhead in our amortized space-time complexity, which is sublinear in the time complexity of the irreversible algorithm. Great. Okay, so now we have this nice transformation. The last thing is that we provide quantum attacks on memory hard functions. So memory hard functions are a cryptographic primitive used for storing passwords. Its security is brought by its high amortized space-time complexity. So the idea is that now we can port over all of the attacks that we've studied before, and now we can have efficient amortized space-time complexity quantum circuits for the attacks, meaning we can employ pre-image search and so on to defeat the primitive. One application of this is an attack on Argon 2I, which was the password hashing competition winner in 2015. But we're able to, our results apply to pretty much all memory hard functions, and you can see the paper for details. Okay, so in this work, we used this pebbling game to be able to construct these quantum circuits with good trade-offs from our original classical algorithms. So what's next? I think one of the more exciting future work for this is on memory hard functions. So classically, there's this nice result that says that we can always map a classical evaluation strategy to a pebbling, a cost equivalent pebbling. This means that pebbling is both an upper and lower bound on the amortized space-time complexity. The natural question is whether or not we can show that reversible pebblings also characterize the cost of coherently evaluating them. In particular, I think that memory hard functions are a promising candidate for breaking through this barrier we seem to have on proving space-time lower bounds for single output functions. So if you have any questions or you want to talk about anything space-time trade-off related, you can email me. Also, feel free to look at our papers. The first one's on archive and the other's on preprint. Thank you.
Any questions?
Thank you for the talk. So I was curious as to how this might compare to, say, like an active volume architecture. I'm not sure if you're familiar with that. So it's essentially a setting. So this is a paper by like Daniel Latinsky and Naomi Nickinson that like considers essentially just the amount of gates, like just the gate volume being relevant to the total computation. And this is achieved through like gate teleportation. So the question is, how worried are you as to whether or not having a bunch of qubits containing garbage sitting around are like actually going to be like a reason for like these computations being difficult to scale?
I see. So yeah, I am not aware of that. But as far as being worried about garbage and scaling it, so I think just in general, like when you compute, especially like very sequential things, you're going to generate a lot of garbage. And for most applications, you can't keep that around because it will mess with the coherence. So yeah, maybe I don't completely understand the question, but I think that, you know, pebbling is a decent tool for making sure you clean up the garbage in an efficient way.
Thank you.
More questions? So if I understood correctly, all this mechanism of pebbling is for implementing classical functions on quantum. So, so first of all, you had this the examples that you studied here are like the taking powers of this classical. Does it also work for more general functions or?
Yeah. So the real thing is that it works for any problem where you have where you can represent your data dependencies as a graph. And so it's true, you can just only use reversible pebblings for like a quantum problem where you are able to map that out. So yeah, it does work in general. That was just like the example I went for. Thank you.
And can you, I mean, suppose I have a quantum function, and maybe it uses resets in the middle. Can I use some of these techniques there? Or?
Yeah, so our reversible pebbling game actually does not, it doesn't characterize these like possible like measuring and stuff like that. I do think it's a very interesting question on how we can kind of represent that in the pebbling game. Now, there's like another pebbling game called the spooky pebbling game that, that uses like intermediate measurements to save some space. So it is an interesting open question whether or not we can combine those two ideas. But as for now, only coherent. Yeah, thank you.
Any more questions? Okay, so thanks to the speaker again.